So I had some personal constraint at home, so I could not teach yesterday, but instead we had a lecture by Chandra, who basically showed you all how to prove the statement of the Schmidt decomposition, which I had stated on in Monday's lecture, right? So let's just quickly recap the statement of the Schmidt decomposition, because that will be important. Any questions on that? So the recording of the lecture has been posted on the same Google Drive. I'll ask Chandra to also post his notes, or I can post earlier notes that I have from previous year's lectures. Maybe I'll just do that. Right. So the idea is that, and this is, by the way, a statement which is specific to bipartite pure states, right? Which means there are two quantum systems in play. There's no constraint on the dimensionality. So it's not a qubit statement, right? It holds for quantum systems of any dimension. But the idea is, given a bipartite pure state, right? There exist orthonormal states, and I think I call them EI. And Fj, so they belong to A and B respectively, such that psi AB can be written as sum over I, lambda I, EI, Fi, right? And this is a very convenient statement because it is via this Schmidt form. So this is often called the Schmidt form. Okay, it is via the Schmidt form that the entanglement content of the state is manifest. And as Chandra mentioned yesterday, if the number of lambda i's here, so let me call this 1 to k. Okay, so I guess he used the term Schmidt rank of a state, right? This is the number of non-zero. So by the way, the lambda I are called Schmidt coefficients. So let me say that first. Lambda I are called Schmidt coefficients. And sum over I lambda I squared is 1. Actually, I'm not sure whether Chandra used a square root here. So did he put a square root lambda I? Yes, no?
No.
No, so it was exactly in this form. Okay, good. And the number of non-zero Schmidt coefficients is what is called the Schmidt rank. And if this is 0, then the state is obviously, sorry, not 0. What should I say? Then is the state unentangled? If the Schmidt rank is?
1.
The rank is 1.
Correct. So if the Schmidt rank is 1, the state is unentangled. And if the Schmidt rank is greater than 1, strictly greater than 1, the state is entangled. And the Schmidt rank is always less than or equal to whichever is the smaller of the two dimensions, right? So this basically puts a bound on how entangled a pair of states can be. That is constrained by the dimensionalities of the two systems, right? I already explained this on Monday. And finally, we can also quantify. So this is what I would call an entanglement witness or a test. This is an entanglement witness or a test. Okay, and you can also then quantify entanglement, which means you can say this state is more entangled and that state is less entangled. So this is often called an entanglement measure. right? And this measure is nothing but the Shannon entropy of this probability distribution comprising the lambda I squared. So the lambda I squared constitute a probability distribution, and the Shannon entropy of this, so this is nothing but minus sum over I lambda I squared log lambda I squared, right? So this constitutes a measure of entanglement. This is often called the entanglement entropy. This is called also sometimes called a subsystem entropy, because as you know, this is the entropy of the density matrix of the reduced states, right? So I hope you saw that the lambda i's are nothing but the, so let me just mention this, the lambda I are the eigenvalues of the reduced density matrices rho A and rho B. Okay. And so they tell you how mixed. So this subsystem entropy basically tells you how mixed is the reduced state. And as we discussed earlier, so this is a measure of how mixed the reduced state is. So the more mixed the reduced state is, the more entangled is the bipartite state, right? Okay, so this sort of recaps and summarizes everything about the Schmidt decomposition. Any questions, please ask me. If not, I will move on to talking about what I've put in the title of the lecture today, namely the idea of purification. So we have seen how to go from a bipartite state to the reduced or the local states. Purification is kind of the converse idea. The idea is that I have some density matrix, okay? And this belongs to some, this is a reduced density matrix on some system HA. Just a small aside and a mathematical technicality, I will often write state psi A belongs to HA. But you will notice that I will never write rho A belongs to HA. Why is that? Can I write this? The quantum Hilbert space or the vector space is a space of vectors, right? Whereas rho A is what?
An operator.
Exactly. So rho A does not belong to the vector space. It's an operator on the vector space. Okay. Just please note this contrast, or just keep in mind this technicality, right? They're both descriptions of quantum states, no doubt, right? But yeah, one of them is an element of the vector space. The other is an operator on elements of the vector space. Okay. Right. So consider some state in some quantum system HA, right? And let's say in general, this is a mixed state, right? This is a density operator. The idea of purification is to say that one can always associate a pure state in a larger Hilbert space with the mixed state. So every rho A on HA can be associated with a pure state on a larger space HA tensor HB. Okay, and this is something which is very useful, right? In fact, this again the origin of this statement, like most statements in quantum information theory, has to do with a fundamental mathematical mapping, right? It's what is in the mathematical terms called an isomorphism, right? So then isomorphism between operators on HA and states on HA tensor HB. So the idea is that you can always append, so given some system A, I can always append another system B, so append or add another system B of appropriate dimension, right? Such that there exists a psi AB which belongs to HA tensor HB, who's marginal, obviously. So what does it mean to say I associate a density operator on a smaller system to a pure state on a larger system? How does that equivalence work? The equivalence works provided the corresponding partial trace or the reduced state. So you should recover essentially the correct marginal state, right? That's when this association is complete. That's when the association makes sense. So how does one do this? I hope the idea of purification is clear, right? And like I said, this goes back to a deeper isomorphism between operators and states. Okay? I'll just leave it here. Those of you who are curious okay, maybe I'll just state what this is called, and I don't know, some of the PG students want to go ahead and explore what this is. This is called the Choi-Jamiokowski isomorphism. Okay. All right. So how does one do this purification? So given this state rho A, I can always write it in its diagonal form, right? So let's say that this is the so-called spectral decomposition or the eigenvalue decomposition. So the lambda I are eigenvalues, the ket i's are the eigenstates, right? This is the diagonal form of rho A. So what is the pure state that one will associate with this? So let's say this is a d-dimensional space. This is a d-dimensional quantum system. So we need a additional quantum system HB to also be d-dimensional. Okay. And then what is the state that one can associate with this? So let us say that ket JB is an orthonormal basis for this additional quantum system that we have appended now. So now what is the so-called purified state? Any ideas? It's the reverse of the Schmidt decomposition, right? In the Schmidt decomposition, you identified a particular way to write the bipartite state. And then you did a partial trace and you find that the reduced density matrices are already in diagonal form. And those eigenvalues are simply the lambda I. Did you or did you not do that yesterday? So this is the reverse of that. Okay, so you're all unusually quiet today. So let me just write down that the corresponding bipartite state must simply be a state of this form. Okay. So yeah, I could have put lambda I squared here, and this would then be lambda I, which is exactly like what you did in the Schmidt decomposition. I don't know whether I made a mistake there in saying that. Yeah. So this should be lambda I squared, I guess, are the eigenvalues of the reduced density matrices. Yeah, so this is how you get the purified state, right? These eigenvalues are positive numbers because this is a positive operator. These eigenvalues are positive numbers between 0 and 1. So essentially you write down a bipartite state in the Schmidt form with Schmidt coefficient square root lambda I, right? And just pick any local basis on B. I've simply labeled it as I, right? But suppose I call these bases as, let's say, Bj, okay? Then this is just Bi. Okay, so let's do a quick example to give you some intuition about this. So let's just take our favorite example of C2, and let me say that rho is simply, yeah, let me take the most canonical example, right? So let me say that this is identity. Okay, what is the purified state corresponding to this on C2 tensor C2? What would be a purified bipartite state for this? Say this is A and this is AB. Yes?
The Bell state.
Very good. So how do you get that? So you just follow this recipe. It's 1 over root 2, right? Pick another basis for C2. So the basis you have picked, by the way, is again 0, 1, right? So you have again picked the 0, 1 basis, and then you will get the state 1 by root 2, 0, 0 plus 1 by root 2, 1, 1. But I want to propose an alternate purification. Let me call this I tilde, which is 1 over root 2, 0 plus 1 over root 2, 1 minus. Is this also a valid purification? How will you check if this is also a valid purification of the same density matrix?
By taking the partial trace.
Indeed. So why don't you guys go ahead and do that and let me know if this also is a valid purification. Check. So what is the reduced density matrix corresponding to this? Yes.
It's the same one. Same thing as above. Half identity.
So this is also half 0, 0 plus half 1, 1. So indeed, this is also a valid purification of the same density matrix. So what does this tell you about purifications? Are they unique? So you notice that I only said you can associate a pure state, right, with a pure state. I did not say that this association was unique, and with good reason. So the moral of the story with this example is that the purification of a given density matrix rho to some pure state on a larger space is not unique. And just to make you think a little bit more, how do we go from this purification to this purification? What has happened between this purification and the second purification that I wrote down, psi tilde AB? Is there a way to transform from one to the other?
In terms of gate,
Yeah.
by applying Hadamard on second particle.
Exactly. By applying a Hadamard on the second system, so if I do this gate operation, which is identity on A tensor Hadamard on B. Okay, now it's a capital H, not the Hilbert space H. I can go to the second state. So the two purifications psi AB and psi tilde AB are related by what is called a local quantum gate or a local unitary. In this example, where you have 1 over root 2, 0, 0 plus 1, 1, and the other purification is 1 over root 2, 0 plus 1 minus, you can go from one to the other. So it's identity on A and Hadamard on B. Okay. So the first purification obviously is an entangled state, it's a Bell state. What about the second purification? Is that also an entangled state? One over root 2, 0 plus 1 minus. Is it an entangled state? Guys, you have to quickly answer me because I'm
Yes, ma'am.
Okay.
It is an entangled state.
And is it in Schmidt form?
Yes.
Indeed. So this is very much an entangled state. Indeed, it is a maximally entangled state because reduced density matrix is identity on one subsystem, and I'm sure you can figure out that if you trace out the first subsystem, what will you get in the second on B? You will get half plus 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 half minus minus. So that's also a maximally mixed state. So this is indeed a maximally entangled state, and it is already in Schmidt form. It is just that the two Schmidt bases are 0 plus, 0, 1 and plus minus. So what does it mean to say that the Schmidt bases are now 0 plus on subsystem A and plus minus on subsystem B? It means that the measurement outcomes are now correlated between these two bases, right? So if you do a measurement in the 0, 1 basis on system A and in the plus minus basis on system B, right? So these measurement outcomes are correlated. So the correlation is manifest in these two bases, the 0, 1 and the plus minus basis. If you were to write this state in the 0, 1 basis, what do you get? So if you were to write down this purification, psi tilde AB, so if you expand this, please expand this and tell me what do you get in the 0, 1 basis? Quick.
1 by 2, 0, 0, 0, 1, 1, 0, minus 1, 1.
Very good. So you see now you have all possible basis states here. So if I were to measure these two qubits, both of them in the 0, 1 basis, are they correlated? So there is no correlation as far as the 0, 1 bases are concerned. It's only when you measure the second qubit, in this case the B system, in the plus minus basis, are the correlations manifest. Is this idea clear? If you measure both the qubits in the 0, 1 basis, all outcomes are possible. All 4 classical outcomes are possible, right? If A were to measure in the 0, 1 basis and get outcome 0, B could still get 0 or 1. If B were to measure, if A were to measure and get 1, then so on and so forth, right? But in this case, if A were to measure in the 0, 1 basis and B were to measure in the plus minus basis, then only 2 pairs of outcomes are possible. If A is 0, B is plus. If A is 1, B is minus, vice versa. Okay? So what the Schmidt basis tells you is, so this is not in Schmidt form. Whereas this is very much in Schmidt form. Okay? It's the same state. The same state, same bipartite state. What the Schmidt decomposition tells you is which is the basis, which is the measurement in which these correlations are manifest. First of all, it tells you whether there are correlations in the state, and second, it tells you which is the basis in which these correlations are manifest. Okay? Questions? Okay, so we decided that the purification is not unique and you can always perform a local unitary operation. I hope you realize that this is a general principle, right? It's just that in this example, I could show this to you very easily. But in general, any two purifications associated with a given density matrix are related to each other by a local quantum gate or a local unitary. Now my question is going to be, is the Schmidt decomposition unique? Okay. Are people still there or not? Okay, so since I see Srihari's name appear first, and Srihari and I discussed this briefly in a meeting a week or so ago. Srihari, are you there? Okay, I don't know if he's around or not. But anyone, is the Schmidt decomposition unique?
No, ma'am.
So again, there is a certain local freedom in the Schmidt decomposition. So just like how we said that as far as this purification is concerned, it is not unique in the sense that you can always apply local quantum gates and obtain two different purifications of the same reduced density matrix. Similarly, you can transform one Schmidt decomposition or one Schmidt form to another via local gates. But of course, note that, so the answer would be that it is unique up to local unitary gates. Okay. Of course, these local unitary gates do transform the state, right? So when I go from this to this, I have applied a certain local gate. I don't call both of these the same state. This is what I call a Bell state. I do not call this a Bell state. However, the extent of correlations in both the states is the same because they are related by a local unitary transform. So the moral of the story is that local quantum gates cannot change the entanglement content of a state. We say bipartite or multipartite state. Okay. So you can change the local bases via local gates, but you cannot change, for example, the Schmidt coefficients. You cannot change the Schmidt rank. You cannot change the entanglement entropy, right? So the Schmidt basis can be changed, but your lambda I squared or the Schmidt coefficients are invariant, right? And so the Schmidt rank and the entropy, the entanglement entropy, do not change. Okay, so please keep this in mind, and I hope you've justified this with some of these examples that I just gave. All right, so finally, I want to talk about this. So this will probably be the last thing I talk about in entanglement, and then I'll move on to gates and circuits starting Monday. So I want to talk about the so-called Bell CHSH test. So remember, we've written down these Bell states, right? So you recall the Bell states. And in particular, let me recall, for example, this state, right? And we said that the idea of these kind of entangled states is that they contain correlations beyond what is possible in classical systems, right? So I said something like beyond classical correlations. Okay, so this Bell CHSH test is a way to quantify this statement. So what does it mean to say that such states have correlations beyond classical correlations, right? So we went back to history and we said that these are also called EPR states because these states, such kind of states were originally visualized by EPR, right? So they wrote down these states to justify that quantum mechanics is incomplete, right? Quantum mechanics as it was then is incomplete, right? And their argument was as follows. So you write down such a state. Now this is what is called a perfectly anti-correlated state, okay? Now, of course, you can think of classical systems which are anti-correlated, right? I can think of two pendulums, right, which I set up the vibration in such a way, or just two oscillators which I can set up in such a way that they are in such an anti-correlated state, right? There's nothing that prevents me from setting up such a system. Now, what makes these kind of states unique is the following fact. So we see that they are anti-correlated as far as the 0-1 measurement is concerned. Now, what does this Bell state look like? So let me just call this phi. Okay, I forget which of the betas this is. So what does phi look like in the plus minus basis? So can you just rewrite these and let me know? So 0 is plus plus minus over root 2. 1 is plus minus minus over root 2. So can you just tell me what this state looks like? The plus minus basis. Okay, I'm just not getting any answers today, so I'm going to proceed with the lecture. So this state looks exactly the same way in the plus minus basis, in the sense that it is perfectly anti-correlated. Okay. Right. So this is a state where the correlations are exactly the same, whether you're in the 0-1 basis or in the plus minus basis. So the point is that if one of the parties were to measure in one basis, they know what the outcome is if the other party were to measure in the same basis, right? But they actually don't know a priori what is the basis choice that the other party is making, right? So despite that, despite the fact that there is a non-locality in play here, right? I can think of these two parties as being in two separate labs, right? They are space-time separated, which means they are sort of outside each other's light cones, as we like to say in physics, right? So they are causally separated, right? But somehow, irrespective of which choice of basis they are measuring in, this party knows what the outcome is if the other party measured in this basis and vice versa, right? So these correlations they kind of seem to uh, suggest that these values of these observables, right, which is the, whether the outcome is 0 and 1 or whether the outcome is plus and minus, right? So the existence of correlations in multiple bases somehow suggests that these outcomes must be predetermined, right? Because it's not as if something happens here and then something happens here. The correlations persist no matter which basis they measure in, no matter which order they measure in, right? So they suggest that somehow these outcomes must be predetermined, right? Suggest that these outcomes must, when I say predetermined, in some sense, it's as if there is something hardwired about the state, right, which should be able to tell us what these outcomes are already before the measurement is even made. But quantum mechanics forbids that, right? So this is, however, in violation or in contradiction with all our known ideas of quantum measurement, etc. Right? In fact, it was repeatedly emphasized that quantum measurement is a probabilistic process and you simply cannot predict, right? So they use these kind of states to suggest that these correlations must exist because there must be something, some hidden information, right? So maybe there is some hidden information which quantum theory is missing, right? Which is what leads to this kind of correlation, no matter which basis or, independent of the choice of measurement, right? So how does one now resolve this kind of a question. It's a very, it's not a question which can be falsified or quantified or answered, but this kind of a question was addressed by John S. Bell in 1964. He was a particle physicist actually, and he came up with a quantitative test, right? Essentially, this is often today thought of a quantitative test for quantum mechanics itself, right? Basically suggesting that these states are actually, you cannot look at these states from our classical intuition. There's something happening in these states which is beyond our classical intuition, right? So what is our classical intuition, so to speak? So classical intuition suggests the following. It suggests that the values that physical properties take are independent of the measurement process, right? So let me not say, let me say that they are inherent to the system, right? And measurement merely reveals these values. So this kind of idea is often called objective reality, right? So the idea is that the act of measurement is not doing anything special. It is simply revealing to you what is already inherent in the system, right? So this is also sometimes simply called realism, right? And the second classical intuition, which as we will show these states violate, is the idea of locality. That physical systems are local, right? In their description, that a measurement in A's lab is completely independent of a measurement in B's lab. So these are independent physical processes, right? Provided A and B are causally separated. As I said, in general relativity, we think of this as light cones, right? That there is a certain light cone, which is a sphere of influence. And if A and B's lab are somehow outside each other's light cones, they're outside their sphere of influence. And so what happens in A's lab is can be described completely independent of what happens in B's lab, right? So this is our classical intuition. And what Bell showed is that if you assume that quantum theory somehow fits this classical intuition, then you cannot have such states. The other way around, if you have such states, then it means that quantum theory does not fit into this box. And so you cannot then argue about the completeness or incompleteness of quantum theory because it's something that exists outside of these assumptions, right? So let me state what the inequality is. Imagine that you have two systems, A and B. I'll just carry on for another few minutes and then stop the lecture. Anyway, I don't see any questions and so on. So I'm just going to proceed. So I have these two classical systems. So let's write down the classical, let me say, so what would classical correlations look like, right? That's what I want to talk about. So imagine you have two systems A and B, right? Or two labs, right? And imagine that there are four physical quantities, P, Q, R, and S, okay? So there are four physical quantities, P, Q, R, and S, which take on values plus or minus 1. Okay, so essentially PQRS are some binary valued observables. So actually, I'm not talking quantum mechanics or classical mechanics at this point. I'm just talking about, let's say, a reasonable physical theory. Okay, and a reasonable physical theory, we say, is one which satisfies these assumptions of locality and realism, right? Okay, so if these are binary valued observables, then each of them can take values plus minus 1, plus minus 1, and I've distributed them between A and B's lab. Okay. Now, this is actually a probabilistic theory. Okay, we are even allowing for it to be a probabilistic theory. Okay, so let's say that this is a probabilistic theory. Then we can write down a certain joint probability distribution and I'm going to call these as little PQRS. Okay, there is a joint probability distribution over the outcomes PQRS of the physical observables or quantities PQRS. Okay, so actually maybe, yeah, I think it's only fair that I stop here, given that it's already 9:55. So let's continue on Monday and let's wrap this up on Monday. Yeah, so the idea is that we'll try to constrain the expectation value of this some function of these observables classically or based on a local realistic theory, and we'll show how the Bell states will violate this kind of an assumption. Okay. All right, so I'll see you all on Monday then.
Excuse me, ma'am.
Yeah.
Ma'am, can you please repeat the announcement that you made in the beginning of the class?
Yeah, so the assignment 2 will be posted tomorrow and midsem will happen on 10th October from 9 a.m. to 12 noon. Sunday, 10th October, 9 a.m. to 12 noon. Okay, I'll also post the announcement on Moodle. Yeah.
Thank you, ma'am.
Sure.
Oh, hello.
Yeah.
Ma'am, just a quick question. I just when you said the purification of the Bell state was a purification of a single qubit state, right?
Yeah.
And then if I consider a GHZ state, it's a purification of a 2 qubit state. So is there any lower bound on the auxiliary space I have to introduce in order to purify a state?
Yeah, indeed. The smallest dimension you need is the dimension of the density matrix. So you're saying like that. Okay, so if I have a bipartite density matrix, you're saying that the GHZ state becomes a purification of that.
Yes,
Yeah,
ma'am.
yeah. That's a good point. So yeah, you can indeed have, I think the smallest dimension you need is just a qubit, right?
Okay.
Yeah, the smallest dimension you will need in any case is a qubit, but you may not always be able to purify using just a qubit. I think the GHD is a very special example, right?
Yes, ma'am, because it was two independent terms we had, it is possible to do with a qubit.
Also, see, the reduced state in that case is again identity, right?
Yes, ma'am.
So when my reduced density matrix is identity on any dimension, then I can always add an additional qubit and make a maximally entangled state, which is just one additional qubit system padded to it, right?
Okay.
But if I don't have an identity all the time, then I may need up to the dimension of the space itself. right?
Ma'am, the reduced density matrix will be a 4 cross 4, right? So with 2 ones on extreme diagonal
That's
points.
the specific case of, oh, I see. So you're saying it's not
Yes,
identity
it's not
actually. It's
identity.
just,
Yes. It's like
yeah, the
one on the
reduced,
corners.
yeah. The reduced state in that case is 0, 0 plus 1, 1. Is it?
Yes, ma'am. 0, 0 and 1, 1. So with
Yeah,
2 ones.
yeah. Yeah, it is not indeed a maximally state. Yeah, so I would say this is a special example, because if you take something like a density matrix which has, say, 0, 0, 0, 1 and 1, 1, right?
Okay.
Then it's not clear that you can simply purify it with just a qubit,
Yes,
right?
yes. Yes, ma'am. You cannot.
So I think the general thing is when you have, this is a very special example, and I think it's only for the GHZ that this happens.
Okay. Okay.
Yeah, I'll have to think about this a bit more actually. It's an
Yes.
interesting point that you bring up. Yeah, you don't always need the dimension of the reduced space,
Okay.
right?
We
But
might need less.
yeah, you could do with less, in this case just a qubit, but that's not always the case.
Okay. Okay. And also again with the same state, like for Bell state, even if we change the basis, we somehow get the same sort of structure for the Bell state.
Yeah,
But then the GHZ state again in a different basis would be like we'll not have the same number of terms.
correct. Yeah,
Uh,
yeah,
s-
yeah.
so how do we quantify the entanglement in that case when the number of terms is going to increase?
No. So the GHG state does not have correlations in all bases. That's a
Right.
speciality of
Okay.
the Bell state. That's what I was
Okay.
trying to highlight in the end. So what I said is, first of all, you see the Schmidt form is only for bipartite states. You don't have a Schmidt idea of a Schmidt decomposition
Right. Right. Yes. Oh,
for
sorry. Yeah.
yeah, yeah.
Okay.
So
Okay.
you don't
Sorry.
have a Schmidt decomposition for a 3-qubit state.
Okay. Yes. Yes, ma'am.
Though it's very tempting to draw analogies between Bell and GHZ, but it's not the same.
Okay. Yes. Yes. I forgot the bipartite. Yes, ma'am. Thank you. That's
Yeah, sure. Yeah. Okay. So I'll see you on Monday then.